Okay, we are in segment 2 of lecture 30. And as promised, we're going to introduce another type of reactors known as membrane reactors. The term membrane reactor describes a number of different types of reactor configurations that contain a membrane. Of course, you are familiar with membranes. They are used for separation, right? So you pass a stream with given components, and only a component or two passes through the membrane and the remaining stays there. Okay. Okay, so let's discuss together reasons for using membrane reactors. Otherwise, we will say, well, let's just use plug flow reactor. It's very simple, very cheap. It's a pipe, right? It's a simple pipe that we can use as a plug flow reactor. Why should we go and buy an expensive membrane reactor, a pipe which is actually a membrane, which actually is good to use because it's rigid, it does not break. At the same time, it can allow some of the products to diffuse out, or some of the reactants to diffuse in. Okay, so, well, there are a few good benefits for using membrane reactors. The first benefit is to increase conversion when the reaction is thermodynamically limited. So, if the reaction is thermodynamically limited, meaning the equilibrium conversion is very small, therefore the conversion that you can achieve is also small. Then maybe the membrane reactor becomes useful here. Let's take this example, which is the steam reforming of methane. We discussed this reaction in chapter 1. So this is a reversible reaction. We can carry out this reaction inside the membrane. Can carry it inside the tubular membrane reactor. So this is the reaction mixture. I'm producing hydrogen, and as I produce hydrogen, the hydrogen diffuses out because it's the smallest molecule among these molecules. So it is the one where it can diffuse easily through the membrane, and it will diffuse due to the concentration gradients. You have high concentration of hydrogen here, low concentration of hydrogen here, so it diffuses out. So you know from Le Chatelier principle for reversible reactions, if you pull one of the products out, right, reduce its concentration, the equilibrium reaction will be shifted forward. So if you were not able to achieve good conversion because the equilibrium conversion was small, then using the membrane reactor will help you to shift the equilibrium forward. Okay, so this is one of the good reasons. Let's look at another reason for using membrane reactor: to increase the selectivity when multiple reactions are occurring. Again, let's go to reforming of methane, but this time it is the partial oxidation of methane. So I'm doing reforming of methane through partial oxidation, and I'm still producing the syngas that I'm interested in. But what could happen? In the presence of oxygen and methane, combustion could occur, and you just simply can waste the methane by combusting it. Let's consider this entrance here of the reactor. So if we have here 100 mole per second methane, I'll need to introduce 50 mole per second of oxygen, correct? According to the stoichiometry. So when I introduce both of them here, so there will be some places where the methane molecules would be surrounded by a lot of oxygen molecules, and this reaction could take place, right? But what can I do to prevent this reaction to happen? Well, the best way is to maintain the concentration of oxygen low everywhere, right? How do I do this? So instead of introducing the oxygen at the entrance, right, let's introduce it through the wall of the membrane. Let's introduce through the wall of the membrane. So still I am introducing 50 mole per second of oxygen, but not all of it at the entrance. I'll distribute it throughout the reactor. Okay, remember, so these are not pipes. These are, we're just saying that I will pass the oxygen at the outside of the reactor. So basically we could have two concentric tubes. So this is one tube and this is the other tube. So I'm introducing the oxygen here, and because of the concentration gradients, you have high concentration of oxygen here, low concentration of oxygen here, so it will diffuse inside. And now we have in every single place low concentration of oxygen, because I did not introduce all this, or the whole 50 mole per second here. So therefore, as if I am promoting this reaction and preventing this reaction from taking place. Right. The last benefit here is that we obtain pure product, right? So if you're running this reaction, or this reaction, and I'm producing hydrogen, and the hydrogen is diffusing out, so I'll get pure product of hydrogen at the outside of the reactor. Okay, we can also discuss about membrane reactors for thermodynamically limited reactions more. We just discuss it now, but I'll leave you read through the coming slides in your complete set of slides. Okay, but simply I would like to say, for such reactions, for this reaction, for example, I could shift the reaction forward by simply diffusing the hydrogen out. Okay, so if we have a reaction, let's write another reaction. A plus B would give you, for example, hydrogen plus C. If this reaction was exothermic reaction, means you have heat here plus heat, of course what you will say, oh, I can still, this is a reversible reaction, I can still increase or shift this reaction forward by reducing the temperature, right? If you reduce the temperature, the reaction will be shifted forward. But however, if I reduce the temperature, then the kinetic will be slow. And if this reaction was endothermic, means you have to add heat, then of course you will say, I will add heat in order to shift the reaction forward. However, adding heat might take you into other complications. For example, cracking the reactants or cracking the product, and you can end up having coke formation. Very large temperatures are also bad, because you'll need to be careful with the construction material and so on. So when it comes to thermodynamically limited reactions, maybe you can get away with this limitation of equilibrium conversion by using a membrane reactor. Okay, let's discuss the main types of the membrane reactors. What are the main types of the membrane reactors? Well, we have what's known as inert membrane reactor. The reactor is packed with catalyst, while the membrane serves as a barrier to the reactants and some of the products, or vice versa. So, do you see the membrane reactor here? So the membrane reactor is an inert. This is an inert. So it's simply a membrane. Okay, if you need a catalyst, then no problem. You can add catalyst inside the tube, inside the reactor, or outside the tube. It's up to you. Okay, so this is known as inert membrane reactor, as opposed to catalytic membrane reactor. Here in the catalytic membrane reactor, the catalyst is deposited directly on the membrane, and only specific reaction products are able to permeate through the membrane. So I do need a catalyst, so you deposit the catalyst on the wall of the membrane. So now the membrane is acting as a catalyst and also acting as a separator as a membrane. So therefore it's called catalytic membrane reactor. Okay, this is an example of a tubular membrane reactor. You think it's a rigid pipe and solid pipe where material cannot perforate, but if you zoom in using, for example, SEM picturing, I'm sure you have learned a lot of SEM imaging in the course property of material, strength and property of material. Okay, so you'll see that there are some pores between the grains of this material, which is made from alumina. This material is made from alumina. It's made from alumina, Al2O3. And the pores are actually 700 nanometer in diameter. So you have 700 nanometer diameter, or 7,000 angstrom. Okay, so now some material can actually pass through the wall of the membrane. Okay, for comparison, let's see, you have the benzene molecules, for example, is 4 angstrom. So you can see this tube, the pore size are pretty large, and some molecules can perforate easily. However, because the opening are not straight, then you will have difficulty diffusing the large bulky molecules, and it will be much easier for hydrogen, for example, to diffuse out. Right, let's look at the CRE algorithm for membrane reactor. We use similar algorithm but with a slight modification. We use the reactor volume instead of the catalyst weight, and then you can convert, of course, weight to volume easily using the bulk density if there is catalyst inside the reactor. Okay, so how should we derive the design equation? Well, let's write hydrogen mole balance for the shown segment of the membrane reactor. So this is actually part of a large reactor, membrane reactor, very long one. We took only a small segment in the middle. Okay, and in the middle we have in the reactor we have this reaction taking place. A is being cracked to B and C, where only B is diffusing through the wall. Tamam. So we have a mixture of A, B, and C here, and then we have a mixture of A and B, C here, but some of B is diffusing out, and the reaction is taking place here, and more B and C is being formed, generated, and more A is being consumed. So let's do a material balance. طبعا you know that if we're doing material balance on hydrogen, which is B in this case, the number of moles of B or hydrogen is not conserved, right? So we'll be producing generating some of hydrogen anyway. So for a non-conserved quantity, the balance becomes input minus output plus generation equals accumulation. So let's write that. So let's take the input to this control volume. The input to this control volume for B is FB, however, evaluated at V, correct? And what about the output? Well, you have FB also leaving here. So not only FB entering, it's leaving also here, output by the flow. So it's minus FB, however, it's exiting at V plus delta V. What else? Well, it's also exiting through diffusion, right? Hydrogen is exiting through diffusion. So how do we quantify this? Well, we quantify it by what's known as capital RB, which is, what is capital RB? Which is the rate of diffusion per unit mass. So the units for RB. Okay, so let's write the unit of RB. So RB has the unit of moles of B diffusing per second per liter. Okay, therefore I'll need to multiply it by delta V. Okay, and one could argue and say, oh well, RB the rate of diffusion per unit volume changes from here to here. And you will ask them why it's changing from here to here. Well, you will say, voila, the diffusion depends on the concentration gradients, right? So I might have more B here, so the diffusion will be here, be large. However, we'll tell them, remember, we're doing balance on a delta V. We have a differential volume, so this differential volume is so small that the concentration of B here is the same as concentration of B here, right? And same thing with A and C as well. The concentration of A here, same as concentration of A here. So therefore, the rate of reaction also is the same everywhere. Okay, so not only RB is the same everywhere, but also the rate of reaction, this RB is the same everywhere. So simply we multiply it by delta V. Okay, so now we account for the other way of output, right? Not only we have output through the flow, but also we have output through diffusion. Okay, plus generation. How do you calculate the generation? Well, we all know that generation can be calculated from the integration of RB dV, correct? This is how you calculate the generation. Evaluated from where to where? Well, it's evaluated from V all the way to V plus delta V. So again, let's integrate this. But we said that this differential volume is very small, and the concentration of A, B, and C is the same everywhere. Everywhere is the same because this is so small, right? This is so small. Therefore, the rate of reaction is the same everywhere. So the rate of reaction is not function of volume. So the RB goes outside the integration. The integration of dV is simply V, right? Simply V, and this V is evaluated from V to V plus delta V, and therefore you will end up with RB times delta V. Tamam? Okay, equals accumulation, and accumulation obviously is 0 because this is a continuous flow reactor which is operated usually under steady state. Okay, so let's continue with the derivation. So let me do one simple thing. Let me rearrange it. So let me write the FB evaluated at V plus delta V minus FB evaluated at V, but because we need to make it correct, we have to put a minus here, so it will be just exactly the same as the above equation. Minus RB times delta V plus RB times delta V equals to 0. Okay, what can we do? Well, this is a useless equation because it contains delta V, and I don't like this. I don't want to, when I design, I don't calculate delta V. Actually, delta V is very small. I want an equation which enables me to calculate V. So let me switch this algebraic equation to a differential equation. How do I switch it? Well, we need to divide by delta V. Okay, so when we divide by delta V, the delta V cancels out here, right? And this goes to 0, correct? And now we have the following equation, that is minus. Okay, let me just write this guy as delta FB over delta V minus RB plus RB equals to 0. Again, this RB is related to the rate of diffusion per unit volume. This RB is the rate of production of B per unit volume. But still, I did not convert it to differential equation. How do you convert it? Well, you'll take the limit where delta V approaches 0, right? And then this will be switched to a differential equation. Right, and let me take, well, let me write it here first. RB plus 2, 0. So this is actually the definition of the derivation, right? The definition of the derivative. Correct? When you have the delta V approaching to 0, this switches to a differential equation, to a derivative. Okay, so can we rearrange? Yes, we can rearrange, and we can actually multiply by negative and then take these two terms to the other side. And we get this equation, dfb by dv equals rb minus rb. Okay, now the question is, how do we quantify rb? How do we quantify rb? Well, you know that rb is related to the rate of diffusion per unit volume, right? Therefore, you will be thinking, maybe I need to go back to the mass transfer course, right? To the mass transfer course, where we're gonna talk more about diffusion. Like, let's do that. Let's talk about the molar flux. Let's talk about the molar flux. Let's talk about molar flux of B. So the more fundamental variable that is more fundamental than RB, which is the diffusion rate per unit volume, is actually the molar flux, NB double prime. Remember the double prime? So this is the molar flux. This is the moles of B diffused per unit time per area, right? And how do we calculate this? Well, as usual, we need to have the coupling coefficient and the driving force, the coupling coefficient and the driving force. So the coupling coefficient is Kc prime, right, which is the overall mass transfer coefficient. Okay, and what's the driving force? Well, my driving force is the concentration of B here. So that's concentration of B, and minus the concentration of B in the sweep channel. This is the sweeping channel. S refers to sweeping channel. Because we are flowing gas here, for example steam, or nitrogen, to sweep the hydrogen away, to sweep the B away. Why is this? Because I want to maintain the concentration of B very small, right? So that diffusion becomes very fast. Correct? Okay, so we said the Kc prime is the overall mass transfer coefficient in meter per second, and CBS is the concentration of B in the sweep gas channel, which is the external channel. Again, we can think about it as a concentric tube here. Okay, let's go back to Kc prime. The Kc prime accounts for all resistances to transport. All resistances to transport. That is, it accounts for the resistance to mass transport from the tube side. So this is the tube side resistance, the tube side resistance of the membrane. So you know that there is a boundary layer here through which there is diffusion. So there is diffusion. So the concentration of B here is the Cb in the bulk, and then there is the Cb on next to the wall, right? And then there is resistance for the mass transport through this boundary layer. What else? There is a resistance for the mass transport through the membrane, right? So we're talking about the resistance in the membrane itself, and here we talk about the effective diffusivity, right? The effective diffusivity. So it's not only the diffusivity of B inside the reaction mixture, which is the case here, but also it has also to diffuse through the pores, right? And what about the third resistance? Well, the third resistance is the diffusion of B from here to the through the boundary layer again to the bulk of the sweeping area, to the bulk of the sweeping area here. Okay, so again there is a resistance for mass transport from here to to here, from here to here. So this is it accounts the resistance in the shell, the sweep gas side resistance. Okay, so obviously we account for this by talking about the diffusivity coefficient, dB, however, on the sweep side. This is the diffusivity of B, however, on the reactor side. Okay, so I sum up all these diffusivities into one overall mass transfer coefficient, which is similar to the overall heat transfer coefficient, which also accounts for the heat transfer resistance in three sequential locations. Okay, so let's go back to RB. So basically RB is written per volume and the molar flux is written per unit area. So how do you convert this to this? Well, simply you need to multiply by area over volume, right, in order to fix the units. So here we cancel out the area. The area we have now moles of B per second per volume for RB. And this ratio is known as small letter A, which is the ratio of the area of mass transfer diffusion. Here, this is the area of the wall. The area through which diffusion is taking place, divided by the volume of the reactor. Okay, and therefore I can write Kc prime times A times Cb minus Cbs. Okay. How can you calculate A? Well, as we said, it's the area, the surface area through which the diffusion occurring. So it is the perimeter here, the perimeter, which is pi d times the length of the whole tube, right? And the volume is calculated by the cross-sectional area. So we have pi d square over 4, multiply also by the length of the tube. Of course, the length cancels out, the pi cancels out, and then you have here the power goes with this d, so you have 4 over d. So this is how you calculate A. Okay, so let's take the product of these guys together and call it Kc. And let's say, voila, the gas, the sweeping gas, which is flowing on the annulus space between the membrane reactor and the other tube, here. Okay, let's say that the sweeping gas is very fast in such a way that the whatever B is diffused and reaches here, it will be swept away, taken away. So the concentration of B in the sweep gas is way smaller than the concentration of B inside the membrane. Therefore, we can neglect this. And now the equation becomes a very simple equation, which is Kc multiplied by Cb. And we were able to write this equation because of, or through our knowledge of mass transfer, which you have studied in separation 1. Okay, so now we are good to go. We have a design equation for the membrane reactor for the species which diffuses out, and we also know how to evaluate RB, which is the rate of diffusion per unit volume, through the knowledge of the molar flux and the K overall mass transfer coefficient and the concentration of B. Okay, now I have a question before we conclude. So this will be our last slide. Why we don't use X when analyzing a membrane reactor? So remember we said there are 4 cases where X is not my preferred variable, right? And one of these cases is membrane reactor. Why we cannot use X to analyze the membrane reactor? Well, let's go to the following definitions. Let's go to X. What is X? X is FA naught minus FA divided by FA naught. Okay, let's look at this membrane reactor. So this is a complete reactor. Okay, so this is volume equals V, volume equals 0. This is volume equals V final. Tamam, and I'm putting A inside because, and I have catalyst, and A will go through this reaction, B is formed, C is formed, but the membrane, the pores of the membrane is so large, tamam, that it allows some of A to diffuse out, some of C to diffuse out, but of course the majority of diffusion is happening for B, which is the smallest out of these molecules, maybe hydrogen. Tamam? Okay, so let's go back to X. Let's see. So if A is decreasing, right? If A is decreasing as you go down the length of the reactor. Why if A is decreasing? Well, there are two reasons. First, A is being converted to B and C. The other reason is that A is diffusing out. So if A is decreasing, not because of conversion only, but because of conversion and diffusion. Therefore, this mathematical equation will be wrong to use to calculate conversion, because if A is not decreasing because of conversion only, but also because of diffusion. So if X is wrong here, right? So all my calculation will be wrong. Type. What else? Let's write if B. So if B equals if A naught times theta B plus nu Bx. So if X is wrong, right, then if B will be wrong as well. Right? If B will be wrong as well. The quantity of if B, tamam, calculated through the membrane will be wrong as well. Right. I have one last question before we finish this lecture. That is, what if A and C are not diffusing out? Tamam? So they are not diffusing out. So now if A is decreasing because A is being converted, right? So this definition is correct. So X is correct. Can I use it here to calculate if B? Well, again, no. We cannot use it to calculate B because the quantity of FB, the molar flow rate of FB through the membrane is affected by two things. The first thing is the conversion, صح? The other thing is the diffusion. So I cannot quantify FB by only looking at conversion. I have to also look at diffusion. So again, this equation becomes wrong to calculate FB, which is a diffusing component. Okay, therefore, Shabab, remember, we said there are some systems where X is not my preferred variable, and this is one of them. We'll meet again, inshallah, in the coming lectures to solve a problem on that. Have a great day.